polynomials, rational functions, z goes to z bar. So let me again make a list. Polynomials, rational functions, then z goes to z bar, z going to real part of z, z going to imaginary part of z, z going to mod z. These are functions we have so far seen. Well, in case of real variable, we have learned so many other functions also. Like for example, we have learned what is sin x. All right. Then we have seen what is cos x and exponential of x and log x and a to x. So this is a special case, but a to the power x for any real number x or sin inverse of x, cos inverse, tan inverse and so on. So these are real functions that we have studied in calculus, and their differentiability properties, like derivative of sin x is cos x, derivative of cos x is minus sin x, derivative of e to the power x is e to the power x. So try to understand that this body of the subject remains same, that we have functions, their domain, codomain properly understood, what values they take, and then their limiting properties, in the sense that you find out limits of these functions, whether they are continuous functions, whether they are differentiable functions, and what is integration of these functions. So this body of the subject, the concepts, they remain same. But what is difference? Difference is that this variable was real. It's a real variable. X was a real variable. Cos x, x was a real variable. E to the power x, x was a real variable. And now the same thing we want to do. That is limit, continuity, differentiation, integration of functions. But which functions? Function of complex variable. That is, we want this replaced by sin z, where z is complex. So we want to learn this now. We'll replace this by what? Cos z. So we need to define these functions for a complex variable. Exponential of z, like exponential of x. So a major chapter in this syllabus is devoted to the definition of these functions for complex variables. That is, the variable is complex. This will come later, and we will define all these functions for a complex variable. That is, we will define sin z, cos z, exponential of z, log z, z to the power w for any two complex numbers. So something like I to the power I we want to define. How does it look? It looks obscure at present. It's not easy to make any sense out of this symbol at present, isn't it? What is I to the power I? But we will define this. In fact, for any z and w, we will define what is meaning of z to the power w. then sine inverse we will define, cos inverse we will define. But at present we postpone that task of defining all these functions. That is definitely one of the important things we want to do in this course. But what can be easily done at present we have done so far. That is, we have done polynomials, we have defined rational functions and these functions. So our stock of the functions at present is restricted to these functions, and this is what it will come. It will come in the course itself. Okay. So the important concept associated with a function is real and imaginary parts of a function, which you can see on your screen there. So suppose now z is a complex number x plus I times y, and if we have fz, that is function of a complex variable, any one of this you may think of, then it is f of x plus I times y. Now when you plug in this value and whatever, because if you operate, you get a complex number. So it will have real and imaginary part. So corresponding to every x and y, you will get some expression in x and y, which I can write as u times xy plus I times vxy. See again. So if you have a complex variable z and a function of the complex variable f, then we want to find value of f at point x plus iy. So that is f of x plus iy. Now you know the function f, so you operate it on this, and when you separate out real and imaginary part, you will get some function uxy of variables x and y, and some other function which we have denoted vxy as function of x and y. Let me give you an example. So suppose, let f of z equal to z square. Then this can be written as x plus iy whole square. Z is x plus iy. That is equal to, yes, x square. Now the iy, so it is minus y square. To xy. Have you understood this? X plus iy into x plus iy. So by using rule for multiplication, it is x square minus y square plus I times 2xy. So this x square minus y square is uxy and 2xy is vxy. So for this function fz, so this fz equal to z square can be expressed as fz equal to uxy I times vxy, where uxy is equal to x square minus y and vxy is equal to 2xy. So we get two functions of two real variables. So we we get two real valued functions of two variables uxy and vxy. So corresponding to fz, that is a complex valued function of a variable, corresponding to a complex valued function of a complex variable we get two real valued functions of two real variables. Those are uxy and vxy. So fz can be always expressed as uxy plus I times vxy. This is very important because we will need these functions to check the differentiability properties of f later on. When we go to differentiation, these functions turn out to be very important. So we will take some examples where we will compute this uxy and vxy like we have done it here for fz equal to z square, where we have x square minus y square is uxy and vxy. So a function also has real part and imaginary part, where real part is a function of two variables and imaginary part is a real function of two variables. So these are two real functions, real functions. So this is a real number. This is real part, of course. This is imaginary part. And this real part of f depends on x and y. Okay? So where z is x plus iy. So z is x plus iy, then fz will have this real part which depends on x and y. So this is a function of two variables. Last year you have learned functions of several variables. So you have learned functions of this type, that is a real valued function of two variables x and y and 2xy. This is 2xy. Let's compute this real and imaginary part of function for some more functions, maybe. Maybe in all these types of functions we will try to compute the real and imaginary part. But then this expression is important. Every complex valued function of a complex variable has a real part which is a real valued function of two real variables x and y, and imaginary part which is again a real valued function of two real variables x and y. So let us compute this for some other functions, say. So let us consider f of z is equal to 5z minus 3i. Okay. It's a polynomial function. This is a polynomial of degree 1. Okay. Now let us compute its real and imaginary part. So for that you put z equal to x plus iy. So put z equal to x plus I times y. These are steps to compute uxy and vxy. So you try to understand it carefully because you will need these functions uxy and vxy later on. So given any complex function, we should be able to find uxy and vxy. And I am telling you the procedure of finding that. So function is given, then you put z equal to this. So what do you get then? Then fz equal to 5 times x plus iy minus 3i. So that is 5x plus 5iy minus 3i. So that is equal to 5x plus I times 5y minus 3. Is this clear? Now see this. So what is uxy? Uxy is 5x. And what is vxy? Vxy is 5y minus 3. So fz we have expressed as uxy plus I times vxy, where uxy is 5x and vxy is 5y minus 3. Let us take one more example. Say fz equal to I times z square plus z plus 1. Put z equal to x plus iy. What do you get? Then fz equal to I times x plus iy whole square plus x plus iy plus 1. That is equal to I times x square minus y square plus I times 2xy, that is this bracket square I have written, plus x plus 1, this 1 I have combined with this real, and I times y. So now I will take real part. So what is real part? This term is I times x square minus y square. So this is equal to, take all the terms in I. So I times, here I have x square minus y square and plus I times 1. This I into I will be minus 1. So this will be real. So now I want this term plus y. Is it clear? So I times x square minus y square plus y and plus this I into I is minus 1. So we have minus 2xy and plus x plus 1. So let me write it. So this is real part and this is imaginary part actually. So it is minus 2xy plus x plus 1 plus I times x square minus y square plus y. Now see, uxy plus I times vxy. So what is uxy? So this is uxy and this is vxy. So we have expressed fz as uxy plus I times vxy. Now I will definitely recommend that you do some practice finding real and imaginary parts of functions. That is, so let me give some exercises. Say fz so equal to z cube plus 1. So find real and imaginary parts. Find real and imaginary parts. Fz equal to z cube plus 1. Fz equal to z plus 1 upon z minus I. How will you do this? Same method, that is you put z equal to x plus Iy. So shall we do this? So let's do this. X plus Iy plus 1 upon x plus Iy minus I. Now how to proceed? Yes? How do we proceed now? We want to find real part of f and imaginary part of f. So you want some uxy, that is some function of two real variables x and y, plus I times some other function, like we have done in earlier cases. So you know that you have to multiply by the conjugate in the denominator. So it is x plus 1 plus Iy upon x plus I times y minus 1. So you multiply both sides, multiply denominator as well as numerator by x minus I times y minus 1 plus 1 Iy upon I times y minus 1 into x minus I times y minus 1 upon x minus I times y minus 1. So you have multiplied by conjugate of this. This is I plus I, here it is minus I. So you have multiplied with the conjugate of the complex value in the denominator. This is equal to x plus 1. Now let us carry out the multiplication in the numerator. X plus 1 into x. So x into x plus 1, and then Iy and minus Iy. So minus I square will be plus 1 and y into y minus 1. So plus y into y minus 1 plus I. So I times xy and x plus 1 into y minus 1 with a negative sign. So minus x plus 1 into y minus 1. So this is multiplication in the numerator. And denominator is, this is z and then this is conjugate, z bar. So what is z into z bar? Z into z bar is always mod z square, you know this. Z into z bar is mod z square. This is x plus Iy, x minus Iy. So it is x square plus y square. So this is square whole square. So whatever is this z, it's mod z square. So this is z. So this is x square plus y minus 1 whole square. So that is how we have written fz. Now what is uxy? So this expression upon this, note that the denominator is real. Therefore actually we have multiplied by z bar. Why have we multiplied by z bar? Because that will give zz bar equal to mod z square, a real quantity in the denominator, and then we can split the numerator as this upon this plus I times this upon this. So this is whatever you can write this upon this part plus I times this upon this part. So this will be uxy and this is vxy. you write down this upon this plus this upon this. This is uxy and this is vxy. So is it clear how to find real and imaginary parts of a function? So I will give you some more problems for practice. So fz is equal to say z bar plus z square. Fz is equal to z bar square plus real part of z plus mod z. So find real and imaginary parts. Let me give one more. 4z square minus 2z plus 1 divided by z plus 1. So find real and imaginary parts. Okay. So I will definitely suggest you that the small exercises that I will keep giving in the lectures, like I have given this, they are very useful, and if you attempt those exercises, then you will have better understanding of the concept that we are learning. There is no alternative to solving problems. Actually, any course, any of your TYBSc course, you will better understand if you solve as many problems as possible. And these exercises will give you chance to solve problems and do computations. Initially we have problems of the computational nature, that is just substitute, now find this real image part. Later on you will have to argue, that is there will be problems of somewhat theoretical nature. That means you apply theorems that you learn. So far we have not done any theorem, so the examples at hand are computational, but they are important. You try to understand the methodology of studying, that is later on we will have theorems, then you will need to understand proofs. And for proofs, initially you will use definitions. So now in the next section we will have limits, continuity, so some definition of limit will come. But then once certain theorem is proved, it is there, and we need to use that either in solving problems or for proving some more statements, so generating some more theorems. So if you look upon the subject from this point of view, that first try to do computational simple problems like we are doing it now, then try to understand proofs of the theorems, and then try to solve problems by using those theorems, some problems of theoretical nature, which also I will give you in course of time. Okay. And then if you understand proofs, you can write down the proofs, and if you can solve the problems by using the theorems, then you have done the job actually, as far as at least that course is concerned. So that is how we are going to progress, that is we will learn step by step, slowly, and I hope you understand. And I want your support only in this regard, or your participation, that you solve problems at home. Whatever exercises I give, you try to attempt those exercises. Initially you may get wrong answers, whatever, you may not get certain problem, that is fine. But every day you need to attempt the problems. So I will definitely recommend that you attempt these problems of finding real and imaginary parts of a complex function. Okay. Now with this we go to certain exercises, okay, which I want to discuss. So these exercises, let me give. All right. So okay. So this is first exercise. The next one is if fz equal to, So you may take down these exercises. Okay. Let me check whether I can give you those right here. So I will give you these exercises so you can see those. Yeah. So see those exercises on your screen. So I am writing the second one. If fz equal to x square minus y square minus 2y, can you see the exercises? Exercise 2, x square minus y square minus 2y plus I times 2x minus 2xy. I times 2x minus 2xy. You see the exercise on your screen. Where z is equal to x plus iy. So z is x plus iy. Now write fz in terms of z and simplify. So write fz in terms of z and simplify. So what is expected here? So now it is the reverse process, that is, just now we saw how to find real and imaginary parts. So z function in terms of z was given and we found uxy and vxy, that is functions in terms of x and y. Now here uxy and vxy are given actually. So fz is already expressed as uxy plus I times vxy. But we want a complex expression, that is expression in terms of z we want now. So we want fz now. How to do that? How to find fz? So uxy, vxy are given. How will you recover z? Symbol z, where z is x plus iy. Here we have in terms of x and y. How will you recover the symbol z? Think for 1 minute. Some expression like this, this is z, this is purely in z. Do you see this? This is in xy, xy. Our earlier procedure was starting with function in z, we got xy, xy, uxy, vxy. Now other way around, this is given, this is given. How will you find fz? That is some expression in z you want to find. Yes? What is x in terms of z and what is y in terms of z? If you understand that, then you can substitute. So that x is equal to z plus z bar. So what is z plus z bar? X plus iy plus x minus iy. So this will get cancelled. So 2x, so divided by 2. So do you see that x is equal to z plus z bar by 2? And what is y? So this is z. So what will be z bar? Let me for your convenience write z bar here. X minus iy. So z minus z bar will be what? Z minus z bar will, x will get cancelled. So iy plus iy, 2iy. So z minus z bar will be 2iy, but we want y. So upon 2i. These formulae are important, remember. These formulae are important. X is equal to z plus z bar by 2 and y is equal to z minus z bar by 2i. One reason is that you can simplify this now and you can substitute x and y. So for example, I can write fz now as, there is x, I can write z plus z bar, okay. bar by 2 whole square minus y z minus z bar by 2I whole square and so on. Okay. So do you understand? Now it is just matter of substituting, and everywhere you will get z, you will not get x and y. So you have found, okay. So plus I times and so on, okay. So you just plug in now. Alright, whatever terms we have. So you get entire expression in terms of z. I mean z and z bar, but that is in dependent variable looks z. Independent variable is z, and then it in terms of z and z bar you get. All right. These two expressions are also important from some other point of view, that is, if in the plane you have equation of straight line. So suppose if I consider equation of straight line in the plane. What is equation of straight line in the plane? What is equation, general equation of straight line in the plane looks like ax y plus c equal to 0. Now when you write this equation, a, b, c are real numbers. So this is how we write a straight line in the plane. This equation, if we want to write in the complex notation, that is notation in terms of a complex number, then these formulae are important. Remember, this anyways is a collection of points xy in the plane. So suppose, let me take a simple example. So y is equal to x. Or this straight line. How does this straight line look like? So it is like this. All of you know this. Okay. So this is point say 1 1, this is 0 0. Okay. So this is 1 comma 1. So this straight line y equal to x is, so this equation represents these points. But we know that this is complex plane also. This every point in the plane can also be looked upon as a complex number. So this point 1 comma 1 which is on this line is actually 1 plus I. This 2 comma 2 is 2 plus I. So this is collection of complex numbers also. You can look upon this line as a collection of complex numbers. So there should be equation of this line in complex variable. Do you understand? So we can say that this is a locus of complex numbers satisfying certain equation in terms of z. So we want this line to be written as z in C, complex plane, satisfying certain complex equation. And in finding this equation, these formulae, they are important. Let us see how we can write this equation in terms of complex variable z. So how will you write x? X is z plus z bar by 2. So x minus y equal to 0 can be written as z plus z bar by 2 minus z minus z bar by 2I equal to 0. I have just substituted x equal to z plus z bar by 2 and y is equal to z minus z bar by 2I. Now let me multiply this by I just to take the clear the denominator. So this is I times z plus z bar minus z minus z bar equal to 0. So what is coefficient of z? It is I minus 1. I minus 1 times z, and z bar, it is I plus 1. I plus 1 times z bar equal to 0. So this is equation of straight line, same straight line, passing through origin and making angle 45 degree. That is this same line, x minus y equal to 0. I have expressed in the complex notation. Very important point. So any curve, this is simplest type of curve, that is straight line I have taken. I have equation in x and y. I can convert that equation in complex variable by using these formulae. So for example, if you have circle, say x square plus y square equal to 4. What is x? Z plus z bar by 2, y z minus z bar by 2. Of course, sometimes we can directly substitute the expression like x square plus y square. I can always write z plus z bar by 2 whole square, okay. But then I know that mod z square is x square plus y square. If z is x plus iy, so if z is x plus iy, then mod z square is x square plus y square. So x square plus y square I can directly mod z square. So this is equation of circle with center at origin and radius 2. Okay. So it is like this. Suppose this radius is 2. Now this circle I have expressed in the complex notation. This is mod z square equal to 4 or mod z equal to 2. You may have some ellipse. Now this ellipse is given means what? Some equation is given. So x square upon a square plus y square upon b square equal to 1. Can you write equation of this ellipse in the complex notation? After all, these can be looked upon as complex numbers, as we saw in these two earlier cases. Yes, we can write this. And how? Just plug in x equal to this and y is equal to this. Done. So you need to just substitute x equal to that, y is equal to that expression, and you get a complex equation. So a conic in particular, we have learned, that is circle, parabola, hyperbola, ellipse, straight lines. And we know that a general second degree equation represents a conic. General second degree equation in two variables x and y, that represents a conic. And x and y you can respectively replace by this and write a complex equation of a conic. Okay. So let me make a general statement like this, that is, by the method described above, we can write the equation of conic in complex variable notation. This is going to be important in a certain topic later on, that is writing the equations of curves in complex notation. Okay. So this was point about this particular formulae. Now you see the problem number 3 there in the notes that you see on your screen, that is find 4 roots of z raised to 4 plus 4 equal to 0. That is now the next problem is you have equation z raised to 4 plus 4 equal to 0. And you want to find 4 roots of this. How will you find 4 roots of this? This equation is z raised to 4 equal to minus 4. So, solution means 4th roots of minus 1. So, you want to find roots of minus 4. Now, how does one find nth roots of a complex number? By using de Moivre's theorem, which we saw last time. I am using the word saw because you only saw that last time, perhaps not heard, but anyways you have learned this in first year BSc. And the formulae is that you first of all express this complex number whose roots are to be evaluated in polar form. That means minus 4 you write as modulus of this. So, modulus of this is plus 4 into cosine of argument of this. Now, what is argument of minus 4? So, minus 4 is here. So, argument is pi. The angle is pi. This complex number, that means minus 4 plus I times 0, makes an angle pi with the positive x-axis. So, this is cos pi plus I sin pi. This mod of minus 4 is plus 4 and argument of minus 4 is pi. Well, actually this is an identity, that is cos pi is minus 1, so minus 4. You can directly check that this is correct. Once you have this, these 4th roots are given by 4 raised to 1 over 4. Now what is this? This is real 4th root of 4. That means every positive real number has a unique positive 4th root, in fact 10th root. Every positive real number has a unique positive nth root. So, it is that 4th root. So, this is a positive real number, and then inside you get cos of, now this is your theta plus 2k pi. So, pi plus 2k pi upon 4 upon 4 plus I sin pi plus 2k pi upon 4. And this k will run from 0 to 3. 0, 1, 2, 3. So, if you substitute k equal to 0, cos pi by 4 plus I sin pi by 4, you will get 1 4th root. k equal to 1, that is cos of 3 pi by 4 plus I sin, and if you put all the 4, you will get 4 fourth roots. So you have solved the first part, okay, the finding fourth roots of 4. The next thing is factorize this polynomial with real coefficients, quadratic factors with real coefficients. So that is next part, that is next part is that you want to factorize this polynomial z raised to 4 plus 4 into what? Into quadratic factors with real coefficients. That is, this is some ax square plus bx plus c, a dash x square b dash x plus c dash, that is 2 quadratics we want. How will you get those quadratic factors? Any idea? Remember that this is polynomial with real coefficient. Therefore, if it has a complex root, then the conjugate is also root. This also you must have seen last time from the notes. Anyways, I have given you the lecture notes of the previous lecture also, where all these points are mentioned, that a polynomial with real coefficient has a complex root, then the conjugate is also the root. So out of these 4 roots that we have, 2 roots must be conjugates of each other, that is, you get pairs. So you must have z1 z1 bar and z2 z2 bar. We understand? So roots of this, roots of z raised to 4 plus 4 equal to 0, that we have actually found. That means you find these roots by just substituting. So you will get 4 complex numbers which are roots. So these roots are of the form some z1, its conjugate will be also root because the coefficients are real, and z2 bar. So when we have roots of a polynomial, we can find factors. So this z raised to 4 plus 4, you can always write as z minus z1 into z minus z1 bar into z minus z2 into z minus z2 bar. Now when you will multiply this out, you will observe that this is z square minus this is z times z1 and this is z times z1 bar. So the coefficient is z1 plus z1 bar times z, z1 plus z1 bar times z plus this minus minus plus, and z1 bar is mod z1 square. Remember, this coefficient is 1, this is z1 plus z1 bar, so imaginary part will get cancelled. So this is also real, this is real, this is mod, so this is real, and this will be again z square minus z into z2 bar and z into z2, so minus z2 plus z2 bar again plus mod z2 square. So z2 bar is mod z2 square, like z1 bar was mod z1. Now this is coefficient is 1, this is real, 1, this is also again real, this is real. So these are quadratic polynomials with real coefficients. So we have expressed z raised to 4 plus 4 as product of 2 quadratic polynomials with coefficients real. Coefficient 1 minus z1 plus z1 bar, which is real, mod z1 square is real, this is 1, that is real, this is real, and this is real. So that is how this polynomial z to the power 4 plus 4 is expressed as product of 2 quadratic polynomials with real coefficients. So this is quadratic with real coefficients. And so also this. So the statement that is used here, you will be able to see in last time's notes, that is a polynomial with real coefficients. Listen carefully, important statement. A polynomial with real coefficients has complex root, then its conjugate is also root. So out of these 4 roots, you must get pairs of this type, Z1, Z1 bar, Z2, Z2 bar. And once you have this, you will get quadratic factors with real coefficients. So that is how you go about solving this. And the problem number 4, as you see in these notes, is a generalization of this problem, that is z to the power n plus alpha can be factorized as polynomials of degree at most 2. See this. You have z to the power n plus alpha equal to 0, where alpha is real. Alpha is real. It is just like this, but instead of 4, you have n, where n is any natural number. And instead of 4, you have alpha. So method should be same, that is you write z to the power n minus alpha. Now solving this equation amounts to what? Finding nth roots of minus alpha. So it is find nth roots of minus alpha. Say n nth roots. So Z1, Z2, Zn suppose. Now here this 4 is an even number, there n is any natural number, we don't know what is that. But because of the same result again, the complex roots will occur in pairs. So if this degree is even, you will get pairs, but if the degree is odd, so if there are complex roots, they will occur in pairs. But if the degree is odd, this pairing is not possible. So you will have to get a real root. And once there is a real root, that means a factor is linear. So for some, say Z1 is real suppose, then Z minus Z1 is a linear factor, factor of degree 1. Therefore it is at most 2 written there, at most 2. So some factors can be degree 1. And then other factors could be of quadratic because they will be paired off like that. So is this clear? That for any arbitrary degree, you can reduce that polynomial, that means factorized, into product of either linear or quadratic factors, provided that the coefficients are real. Coefficients are real, then you can factorize this to product of 2 factors. I will suggest that you go through the remaining exercises because the time is almost over for this lecture, and the remaining exercises are essentially based on what you have done in first year BSc and what we have discussed so far. So it is worth attempting them. There are some problems which need some group theory, but you have done group theory in first semester. Okay. So please do go through these exercises, and then we will meet again next time. We want to learn the notion of limit, but then try to solve these problems, and we shall discuss the solutions of some of the problems in the lectures to come. Next time the notion of limit will be discussed in detail, and what is a neighborhood, what is an open set, and the topological notions will be discussed next.